Okay, 1.7 is on quantified statements. Okay, a quantified statement is a logical statement that includes a universal or existential quantifier. Okay. Example 1. Okay, consider the statements. There exists X such that P of X and not Q of X okay, and for all X, P of X and Q of X, oh, and not Q of X. Okay, let's consider these statements. Okay, where P of X is X is a prime number, and Q of X is X is an odd number. Okay. Okay, for there exists X such that P of X and not Q of X. Okay, so I want a number that is a prime number, but is not an odd number. Does one exist? What's a number that is a prime number?
2.
But is not an odd number? Yeah, 2. So X equals 2 is prime and it's even. Okay. Okay, the example is X equals 2. That proves this true. Since 2 is both prime and odd. Okay. Okay, I should probably formally define what prime and odd are. And if you don't know what prime and odd are, okay, so a prime number has only factors of 1 and itself. Okay, it's only divisible by 1 and itself. Does that make sense? Okay, its only factors are one and itself. Okay, that's a prime number. Okay, what's an odd number? Intuitively, we kind of know what an odd number is, but I mean, what is it? What is an odd number? Like, how would you define it mathematically?
Something that isn't divisible by 2 or gives like a
Yeah,
remainder from that.
yeah, because an even number is divisible by 2. So that's the definition of even, would be that it's it's not divisible by 2. Okay, so it's not divisible by 2. So what does it mean to not be divisible by 2?
You'll have a remainder afterwards.
Say it again.
You'll have like a remainder afterwards.
Okay, yeah.
I don't
Yeah.
kind of, I think that's, yeah.
Yeah, no, I mean, it's good. I mean, you're on a good train of thought there. Okay. In math, we formally define an odd number as 2k plus 1, where k is an integer, is any integer. Okay, it's because we take 2, anything that's a multiple of 2 is even, and we just add 1 to it. Okay. So prime number only has factors 1 in itself. Well, 2 has factors 1 in itself. But it's also, okay, it's also not odd, which means that it's even. It's also even. And I should say not odd. This should say it is. Okay, both prime and not odd. Even. Okay. Okay, there exists for all or for every x, p of x, okay, and not q of x. Okay, is this true or false? Well, again, p of x is prime and q of x is odd, so not q of x is even. So we're saying that all prime numbers are even. Okay, that's a big no. Okay, why? Why is that a no? Give me a prime number that's odd. Well, any prime number other than 2 in existence, right? Okay, 7, 11, 61, just 17, 13, 37, 33, they go on forever. Okay, so the counter example, x equals 3, okay, proves this false. Since 3 is both prime and odd. Right? Okay. Okay, if we are written for every x p of x and q of x, notice that this is not in parentheses. So the quantifier only goes with the p of x. Only p of x is quantified. Okay. Okay, the variable x in the p of x is called the free variable, or it's called a free variable, I should say, a free variable. Okay, it's called a free variable since it can take on any value in the domain. Okay. So x is a free variable since it can take on any value in the domain. Okay, the variable x in for all x p of x is called a bound variable because the variable is bound to a quantifier. It's bound to a quantifier. Okay. Okay, for all x, p of x, and q of x is not a proposition. Since q of x could either be true or false. Okay, not bound. Okay, so it's not a proposition. Okay, but here's the big but. Okay, but for all x, p of x and q of x is a proposition since it has a definite truth value. Example. Okay, given. Okay, p of x is x came to the party. And q of x, or sorry, let's do s of x. S of x was sick. Okay, so we have certain people in a domain. These are people that come to a party or don't come to a party. Maybe they're from our school. okay, and okay, so if I wanted to express, okay, everyone was not sick, how would I express that? Everyone was not sick. Well, that would be a for all X, and then we want a not sick, not sick. Okay. Okay. Example 3. Okay, last example. Given n of x, x is a new employee, and d of x, x met their deadline. Why it says it's, it should be there. Because only people are employees, and people are theirs, not its. So, okay. Okay, so let's look at a truth table for the employees that we're talking about. Okay, so we have name, and then n of x and d of x. Okay, their name, are they new, and did they meet their deadline? Okay, so we have happy, sleepy, grumpy, and bashful. Okay. I sometimes wake up grumpy, and I sometimes let her sleep. You'll get that in a little bit. Okay, so name, happy, sleepy, grumpy, bashful, n of x, okay? Is happy a new employee? No. Is sleepy a new employee? No. Is grumpy a new employee? Yes. Is bashful a new employee? Yes. Okay, did happy meet its deadline? Or their deadline, I should say. Okay, no. Did sleepy meet their deadline? Yes. Did grumpy meet his deadline? No. Did bashful meet his deadline? No. Okay. Okay. So let's look at this statement here. Okay, there is a new employee who met their deadline. Okay, there's a new employee who met their deadline. Is that true or false? Okay, this is false. Why? Let's write it in symbolic logic form. There exists x such that n of x and d of x occurred together. Okay, this is an and statement. N of x happened and d of x happened, and there exists that, right? Well, if I take n of x and d of x, okay, and I do my values on that, okay, there is no true. There's no true. There's no, for all of these employees, no true exists. Okay. So therefore, it's false. Okay, this is false. since no new employees met their deadline. Okay. Okay, B. There exists X such that, okay, n of X, oops, implies d of X. Okay. Okay. Is this a true statement or a false statement? Well, you actually have to look at all of the employees. Okay. We can say, okay, let's add our column over here. N of X implies D of X, right? Okay. So F implies F, that's true. Doesn't matter what N of X is, it's going to be true. Okay. If it's not a new employee, then did they meet their deadline? I don't. No, it doesn't matter. It doesn't matter if they're not a new employee. It doesn't matter if they met their deadline or not, because this is only valid for new employees. Okay, this logic. F of T is still true. T of F is false, and T of T going to F is false. Okay, however, it says there exists an X such that N of X going to D of X, is there one of these employees, at least one employee where this is true for, where this logic statement is true? And yeah, Happy and Sleepy, they're not new employees. Okay. It would only fail if every single value here was true. If all of them were new employees, it would only fail if all of them were new employees and every single new employee, or every single employee, if all of them were new and every single employee didn't meet their deadline, okay, then it would be false. Okay, but we have to look at every single employee in the company and see if they were both new and they did not meet their deadline. Otherwise, this is a true statement. There exists one value that works. Okay, so this is true. Okay, this is a true statement. Since there exists at least one employee who is not new. Okay. Okay, and I'll let you think on that more.